This is a video on osmotic pressure. Osmotic pressure is another colligative property that we'll be studying in this class. The first two that you've studied were boiling point elevation and freezing point depression. Well, osmotic pressure is just another one of those colligative properties. As you recall, colligative properties are those properties which depend upon how much of a solute is dissolved in the solution and not what the identity of the solute is. So you'll get the same result in terms of changing the pressure of osmosis or the boiling point elevation or the freezing point depression. You'll get the same result regardless of what you dissolve in the solvent. The only thing that's important is the concentration. So, we're going to be studying osmotic pressure. Osmotic pressure deals with the process known as osmosis. Osmosis is the selective passage of solvent molecules through a porous membrane from a dilute solution to a more concentrated one. This is a container that has two liquids in it. The two liquids are separated by what are called a semi-permeable membrane. We have the liquid on the left, which is attached to a tube, and the liquid goes up into the tube, and then we have the container on the right, which also has another tube attached to it, and the liquid goes up into there. On the left hand side, we have a liquid which actually may be a dilute solution. It can be a dilute solution, or it can possibly be just pure solvent. On the right hand side, we have a solution which is more concentrated. So on the left hand side, we either have pure solvent or a dilute solution, and on the right hand side we have a solution which is more concentrated. Most likely that the solutions are made up of the same solute. So as we sit here and look at this container and this drawing, we see this arrow. What this arrow is trying to show us is that solvent molecules pass through this semi-permeable membrane from the dilute side, which is of higher vapor pressure, through the semi-permeable membrane to the more concentrated solution side, which has a lower vapor pressure. Remember, the vapor pressure is dependent upon the concentration. The more dilute it is, the higher the vapor pressure is going to be, and the more concentrated it is, the lower the vapor pressure is going to be. So the solvent molecules travel from an area of high vapor pressure to an area of lower vapor pressure through the semi-permeable membrane. The semi-permeable membrane allows the passage of those solvent molecules but blocks the passage of the solute molecules. And what we're going to do is we're going to skip over the next definition for now and show you this close-up of a semi-permeable membrane. Somehow, some way, and it's not really completely and totally understood, is that a semi-permeable membrane is selective in terms of what molecules it allows through and what molecules it won't. So it'll let the solvent molecules pass, but it won't let the solute molecules pass. And again, the solvent molecules are moving from an area that is dilute with higher vapor pressure to an area with lower vapor pressure. The definition above states that the osmotic pressure is the pressure required to stop osmosis. Well, if we look at our containers again, we see that the level of the liquid in the tubes has changed. That's because solvent molecules are moving through the semi-permeable membrane from an area of higher vapor pressure where the solution is dilute to an area of lower vapor pressure where the solution is more concentrated. So as the molecules move through, they push liquid up the tube. The difference in the levels of the heights between the tube on the right and the tube on the left represents the osmotic pressure. Again, the osmotic pressure is the pressure required to stop the osmosis. So in other words, if a pressure equal to the osmotic pressure pi is placed on the liquid in this container, it will prevent the molecules from going through, and therefore it will stay pretty much the way it is. The measure of that pressure required to stop osmosis is known as the osmotic pressure. Here is a similar situation in which we're going to see a phenomenon that occurs based upon differences in vapor pressure. On the left-hand side, we have solvent. On the right-hand side, we have a solution. Now, the solvent and the solution are contained in different containers, and they're placed in one larger container, and they're allowed to evaporate. Remember, on the left-hand side, since the solvent contains no solute, doesn't contain any solute, it's of higher vapor pressure. And on the other side, the solution has a lower vapor pressure because it contains more solute, obviously, than the solvent does. Evaporation is going to occur, but basically the big transfer, the net transfer that occurs, is that the solvent on the left-hand side with higher vapor pressure transfers over to the right-hand side to the solution of lower vapor pressure. And as we saw, it's very similar to osmotic pressure and osmosis, because we saw that the solvent molecules traveled through the semi-permeable membrane based upon the fact that they are moving from an area of higher vapor pressure to an area of lower vapor pressure. Now, there is an equation associated with osmotic pressure, and that equation looks like this. Osmotic pressure pi is equal to m times r times T, where m is the molarity of the solution, r is the ideal gas law constant, and that is the value 0.0821 liter atmospheres per mole Kelvin, and T is the temperature in Kelvin. Now, what is the purpose or the use of this equation for osmotic pressure? Well, like boiling point elevation, and in particular freezing point depression, it's very useful for determining the molar mass of the solute. If we do an experiment in which we can measure pi, the osmotic pressure, at a given temperature, T, if we know how much solute that we use in the solution, we can figure out the molar mass of that solute. Because knowing pi and knowing T, we can figure out m, the molarity. If we know the molarity and we know the mass of the solute in the solution, we can figure out the number of moles, and therefore we can figure out the molar mass. Because remember, the number of moles is equal to the molar mass divided into the number of grams of solute. Now, I'm going to tell you right now, this is going to be one of your most favorite videos. And you know why this is one of your most favorite videos? I'll tell you why. Because this video is over. Yes, that's all there is. It's one of the shortest videos that you'll have to watch. And it's over. And I'm going to end it. And have a good night. And I'll see you in class tomorrow. Bye-bye.